Now the fourth important progression that we have is an AGP, which is Arithmetic-Geometric progression. Now in this progression, every term will have two parts. One of the part will be an AP, while the other part will be in GP. So each term is a product of an AP and a GP. So we can write this progression as A plus D into R, A plus 2D into R square, A plus 3D into R cube, where this A plus D, A plus 2D and A plus 3D, it represents the AP part, and 1 R, R square, R cube, it represents the GP part. So in this, common difference is D and common ratio is R. So generally we can write its nth term as A plus n minus 1D into R to the power of n minus 1. So basically in an AGP, this linear growth is multiplied by an exponential growth, which is very common in advanced summation problems. So if we take some examples of common AGP patterns, so it could be 1 plus 2x plus 3x square plus 4x cube. So here 1, 2, 3, 4, it is an AP, and 1x, x square, x cube, it is a GP. Now we'll see how to find sum of an AGP. Now to find sum of an AGP, we'll basically use the same method which we have used for a geometric progression. We'll take this sum as S and we write this as A plus dr, A plus 2dr square up to A plus n minus 1d into R to the power n minus 1. We'll write the same series again, shifting it by one term. So it will be this A. This is A plus dr, A plus n minus 2d, R to the power of n minus 2, and then plus A plus n minus 1d, R to the power of n minus 1. Now again, as we did for GP, we'll multiply it with its common ratio R. So it will be this R, here will be this AR, R square, here will be R to the power n minus 1, and this one will be R to the power n, and we'll subtract this second series from first. We can write 1 minus RS will be this A plus. Now here AR will cancel, so we'll get this as dr. Here A plus dr square will cancel, we'll get this as dr square. And in the end, we'll have this as dr to the power n minus 1. And then minus this last term, which is A plus n minus 1d, R to the power n. Now this is nothing but a GP containing n minus 1 terms. So we'll use formula for sum of a GP. So we'll get this as 1 minus RS. That'll be this A. Now sum of a GP is A into 1 minus R to the power n. And n in this case is n minus 1 upon 1 minus R. And this is minus A plus n minus 1d, R to the power n. And we'll divide everything with 1 minus R, and we can write this sum as A minus A plus n minus 1d, R to the power n upon 1 minus R. We have written these two terms together, and plus dr into 1 minus R to the power n minus 1 upon 1 minus R whole square. And clearly, this is true when R is unequal to 1. So this is your partial sum for AGP. And if we have an infinite AGP, we'll know this sum will converge if this limit n tends to infinite Sn, it will converge. And we know that we have n with r to the power n. So when n tends to infinite, r to the power n, it converges to 0 if mod of r is less than 1. So infinite GP, sum will converge if r lies between -1 and +1. Then in that case, all the terms containing r to the power n will be 0. So this term will be 0 and this term will be 0. So we'll get sum of an infinite AGP where r lies between -1 and +1 as a upon 1 minus r plus dr upon 1 minus r square.
Now the next question is, we need to find the sum of the first n terms of the sequence Sn, which is 1 plus 2 into 1 plus 1 by n plus 3 into 1 plus 1 by n whole square, 4 into 1 plus 1 by n whole cube up to, and the nth term will be n into 1 plus 1 by n whole to the power n minus 1. Now it's an AGP, and for an AGP what we'll do is we'll write the series again and we'll multiply the series with its common ratio, which is 1 plus 1 by n, and we'll displace the series by one term. So here it will be 1 into 1 plus 1 by n, 2 into 1 plus 1 by n square, and then in the end we'll have this n into 1 plus 1 by n whole to the power n. Now what we'll do is we'll subtract this second series from first. So we'll get minus 1 by n Sn, and here it will be 1 plus, and this is 1 plus 1 by n. This is 1 plus 1 by n whole square. I'll go all the way up to this term, which is 1 plus 1 by n whole to the power of n minus 1 minus n into 1 plus 1 by n whole to the power n. Now it is nothing but a GP with first term 1, common ratio 1 plus 1 by n, and number of terms n. So it will be this minus 1 by n Sn will be a, and then r to the power n, which is 1 plus 1 by n to the power n minus 1 upon r minus 1. So it will be 1 plus 1 by n minus 1 and minus n into 1 plus 1 by n whole to the power n. Now this 1 and 1 will cancel. So we'll get this as minus 1 by n Sn, and here it will be this n 1 plus 1 by n whole to the power n minus n, and then minus n into 1 plus 1 by n whole to the power n. Now it will cancel. Now we'll take this minus n on the right hand side. We'll get this Sn as n square. So sum of first n terms of the sequence is n square.
Now in the questions we need to find this infinite sum, which is 1 square plus 2 square by 7 plus 3 square by 7 square plus 4 square by 7 cube plus 5 square by 7 to the power 4 up to infinite. Now what we'll do is we'll write the series once more and we'll multiply with common ratio 1 by 7, and we'll shift it by one term. So it will be 1 square by 7 plus 2 square by 7 square, 3 square by 7 cube, and so on. Now we subtract second from first, we can write 6 by 7 s, and it will be this 1 square, and then here will be 2 square minus 1 square upon 7, 3 square minus 2 square upon 7 square, 4 square minus 3 square upon 7 cube up to infinite. So it is 6 by 7 s, and this is 1 plus 3 by 7 plus 5 by 7 square, 7 by 7 cube up to infinite, which is nothing but an AGP. Now again, we'll use the standard process. We'll multiply it with common ratio 1 by 7 and shift it by 1. So we can write 6 upon 7 square s will be 1 by 7, 3 by 7 square, 5 by 7 cube up to infinite, and if we subtract, we'll get 36 by 49 s, and here will be 1 plus 2 by 7, 2 by 7 square, 2 by 7 cube up to infinite. Now this is nothing but a GP. So we can write 36 upon 49s, and this is 1 plus A upon 1 minus R. So it will be 2 by 6, 1 by 3. 1 plus 1 by 3 is 4 by 3. Now this is 9. So this S will be simply 49 by 27. So sum of the series is 49 by 27, and that's your option C. Now here the question is, find the value of this sum, which is this summation. K varies from 1 to infinite. This sum n varies from 1 to infinite, k upon 2 to the power of n plus k. Now here the variables are independent, so we can write k varies from 1 to infinite, k upon 2 to the power k into this summation n varies from 1 to infinite, 1 upon 2 to the power n. Now this is an AGP and this is a simple GP. If we solve this GP, it is 1 by 2. 1 by 2 square, it is an infinite GP. First term is 1 by 2. Common ratio is also 1 by 2. So value of this summation is simply 1. And if we solve this AGP, this sum, it is 1 upon 2, 2 upon 2 square, 3 upon 2 cube, and we write s by 2 as 1 upon 2 square, 2 upon 2 cube, and we subtract, we'll get s by 2, and this is 1 by 2 plus 1 by 2 square plus 1 by 2 cube, which again is a GP whose sum is 1. So value of this sum is simply 2, and that's your option D. Now here the question is, we are given this infinite series which is 1 into 3 upon 2 plus 3 into 5 upon 2 square plus 5 into 7 upon 2 cube up to infinite. So this series is actually 3 by 2, 15 by 2 square, 35 by 2 cube up to infinite. Now we'll write this series once again and we'll multiply its common ratio 1 by 2 and we'll displace this series by one term. So there will be 3 upon 2 square, 15 upon 2 cube up to infinite, and if we subtract, we'll get this s by 2 as 3 by 2, and it will be this 12 upon 2 square plus 20 upon 2 cube up to infinite. We'll need to write one more term. Now the next one is 7 into 9 upon 2 to the power 4. So it will be this 63 upon 2 to the power 4, and this is 35 upon 2 to the power 4, and this is 28 upon 2 to the power 4 up to infinite. Now again we write the same series and multiplying it with its common ratio 1 by 2 and displacing it by one term. So it will be this s upon 2 square, and this is 3 upon 2 square, 12 upon 2 cube, 20 upon 2 to the power 4 up to infinite, and we subtract this, we get s by 4, this is 3 by 2, this is 9 by 4 plus and here will be this 8 upon 2 cube, 8 upon 2 to the power 4 up to infinite, and this is nothing but an infinite GP. So we can write this as S by 4, and this is 6 by 4 plus 9 by 4. It will be 15 by 4 plus, and sum of an infinite GP is A. First term is 1 upon 1 minus, and common ratio is 1 by 2. So it will be S by 4 equals 15 by 4 plus 2, which is 23 by 4. So value of S is 23. So sum of this series is 23. Now here the question is, we are given two series and we have to find the sum of this third series, which is 1 plus 3ab plus 5ab square up to infinite. Now this x is 1 plus 3a plus 6a square plus 10a cube up to infinite. Now what we'll do is, we'll write this series again and we'll multiply every term with a, and we'll displace this term by 1. So we'll get this a, and this is 3a square. Next one will be 6a cube up to infinite, and we'll subtract second from first. We'll get 1 minus ax, and will be equal to 1 plus 2a plus 3a square plus 4a cube up to infinite. Now this is an AGP. Now we'll write the series again and again, multiplying it with a and displacing by one term. So we'll get a into 1 minus ax, and here will be this a, and this is 2a square plus 3a cube up to infinite. Now we subtract second from first, we'll get 1 minus a square into x, and here will be this 1 plus a square plus a cube up to infinite, which is an infinite GP, which is a upon 1 minus r. So from here we can write x as 1 upon 1 minus a cube, and from here we can write 1 minus a is x to the power minus 1 by 3, or a is 1 minus x to the power minus 1 by 3, and that's our first result. Now this second series is y equals 1 plus 4b plus 10b square plus 20b cube up to infinite. Now again we'll multiply it with its common ratio b and displace it by 1. So we'll get by will be equal to b plus 4b square plus 10b cube up to infinite. So it will be this 1 minus by, and this is 1 plus 3b plus 6b square plus 10b cube up to infinite. Now this series, it is same as this first series, 1 plus 3a plus 6a square plus 10a cube, and we know that answer to this series is 1 upon 1 minus a cube. So answer to this series will be 1 upon 1 minus b cube, or y is simply 1 upon 1 minus b to the power 4. From here we can write b as 1 minus y to the power minus 1 by 4, and that's our second result. So we have the value of a and b. Now we have to find sum of this series, which is 1 plus 3ab plus 5ab square up to infinite in terms of x and y. So again we write the same series and multiply it with common difference ab and displacing it by 1. So it will be this ab, and this is 3ab square up to infinite. Now we subtract second from first, we'll get 1 minus ab into s, and there will be 1 plus 2ab plus 2
AP whole square up to infinite, and this is nothing but an infinite GP. So we can write this as 1 minus AB into S, and this is 1 plus, and this is 2AB upon 1 minus AB, which is 1 plus AB upon 1 minus AB. We can write this as 1 plus AB upon 1 minus AB whole square, where A is 1 minus x to the power minus 1 by 3 and B is 1 minus y to the power minus 1 by 4. If we put the value of A and B, we'll get the value of S in terms of x and y, which is what we need to find in this question.
Now there's some special AGP sums which we must keep in mind to save time and effort. So special AGP sum is this first one, which is 1 plus 2x plus 3x square up to nx n minus 1. Now we can get this sum using result of a GP. We know that 1 plus x square up to x to the power n will be 1 minus x to the power n plus 1 upon 1 minus x. Now if we differentiate this, we can write 0 plus 1 plus 2x plus 3x square plus nx n minus 1. And this is the required series that we need. And we'll get this result simply by differentiating this with respect to x. 1 minus x to the power n plus 1 upon 1 minus x. So for this series, we'll just need to differentiate this. Now for infinite version, we know that 1 plus x square up to infinite, where x lies between minus 1 and plus 1, it is a upon 1 minus x. If we differentiate this, we'll get this as 1 plus 2x plus 3x square up to infinite, and here will be 1 upon 1 minus x whole square. Sometimes they may ask you the shifted version also. So they could give you the series x plus 2x square plus 3x cube up to infinite. So if we multiply the series with x both sides, we'll get this series as x upon 1 minus x whole square. So if there are certain basic AGPs, we can get them by differentiating a geometric progression. And sometimes we can simply use the summation to simplify an AGP. Say we have this an plus b into r to the power n. So we can split the summation. So it will be this a and then summation n r to the power n plus b summation r to the power n. Now this is nothing but a GP, and this is an AGP, which we generally get by differentiating a GP. Now here the question is, we need to evaluate this double summation. M varies from 1 to infinite. This summation n varies from 1 to infinite, and let this be S, and this is m square n by 3 to the power m n into 3 to the power m plus m into 3 to the power n. Now what we'll do is we'll divide everything with m square n. We can write this as this sum as summation m varies from 1 to infinite, n varies from 1 to infinite, and this is 1, and we'll split as m and mn. So there will be 3 to the power m by m, and this is 3 to the power m by m plus 3 to the power n by n. Now let 3 to the power m by n be am, and 3 to the power n by n be an. So we can write this sum as this summation m varies from 1 to infinite, n varies from 1 to infinite, 1 upon am, and this is am plus an. Now basically we'll write this as smn. If we write snm, it will be this summation n varies from 1 to infinite and summation m varies from 1 to infinite, and this is 1 upon an, and this is an plus am. Now we know that in summation variables are just dummies. So basically this is s and this is also s. So if we add them, we can write 2s will be equal to this summation m varies from 1 to infinite, summation n varies from 1 to infinite. Now we'll take 1 upon am plus an common, and we'll get this as 1 upon am plus 1 upon an. Now this is this summation 1 upon am plus an, and will be this am plus an upon an. Now this am plus an will cancel. So we can write this sum as 1 by 2. This summation n varies from 1 to infinite, summation n varies from 1 to infinite, 1 upon am into an. So basically this is this sum s, and this is 1 by 2. And since m and n, they are now independent, so we can write this summation m varies from 1 to infinite, 1 upon an into this summation n varies from 1 to infinite, 1 upon an. So basically we need to find this summation m varies from 1 to infinite, 1 by am, and 1 by am will be m upon 3 to the power m, and this is this summation n varies from 1 to infinite, n upon 3 to the power n. Now we'll use this result, which is, we know that summation x to the power r, where r varies from 0 to infinite, it is 1 upon 1 minus x when mod r is less than 1. And if we differentiate this, we can write summation r varies from 1 to infinite r x to the power r minus 1 will be 1 upon 1 minus x square, or if we multiply with x, we can write r varies from 1 to infinite r into x to the power r will be x into 1 minus x square. Now for this one, x is 1 by 3, and here also x is 1 by 3. So this s will be this 1 by 2, and this is 1 by 3 upon 1 minus 1 by 3 square, and this also is 1 by 3 upon 1 minus 1 by 3 square. So this sum will be 1 by 2, 1 by 9, and this is 4 by 9 into 4 by 9. Now this 9 will cancel, so it will be this 9 upon 32. So sum of this series is 9 upon 32, and that is the answer to this question. Now here the question is, we have this sequence where a0 is equal to a1 and it is 0, and we are given that an plus 2 is equal to 2 times an plus 1 minus an plus 1. Then we need to find this summation n varies from 2 to infinite an upon 7 to the power n. Now what we'll do is, we can write this recurring relation as an plus 2 minus an plus 1, and it will be equal to an plus 1 minus an plus 1. Now if we put n as n minus 1, we can write an plus 1 minus an It'll be equal to an minus an minus 1 plus 1. I'll continue up to a2 minus a1, and this is equal to a1 minus a0 plus 1. Now, if we add them all up, these terms, they'll cancel. Now, a1 is 0 and a0 is also 0. So we can write an plus 2, it is equal to an plus 1 and plus, now this is 1 plus 1 plus 1. Now this starts from 1 to n plus 1. So it'll be this n plus 1. So from here we can write an plus 2 minus an plus 1 will be equal to n plus 1. So we have another recurring relation. Now from this recurring relation we can write an plus 2 minus an plus 1. This is n plus 1. An plus 1 minus an will be this n, and it'll go up to a1 minus a naught will be this 0. If we again add them all up, so we'll get this result as an plus 2, a1 is 0, and this is 1 plus 2 plus 3 up to n plus 1. So this is sum of first n plus 1 numbers. So it'll be this n plus 1, n plus 2 by 2, or simply we can write an, it will be n into n minus 1 by 2. So we have our an as n into n minus 1 by 2. Now we need to find sum of this series, which is this summation. N varies from 2 to infinite an by 7 to the power n, which is this summation. N varies from 2 to infinite, and this is n minus 1 by 2 into 1 by 7 to the power n. Now we know that 1 plus x square up to infinite, this is 1 upon 1 minus x when x is less than 1. So basically this is this summation x to the power n, where n varies from 0 to infinite, and this is 1 upon 1 minus x. Now we differentiate this, we can write this summation nx n minus 1, and it'll be equal to minus 1 upon 1 minus x square into minus 1. So there'll be 1 upon 1 minus x square, where n varies from 1 to infinite. And if we differentiate this again, we can write this summation n minus 1 x to the power n minus 2 will be equal to this minus 2 minus 1. So there'll be 2 upon 1 minus x cube. Now we need n minus 1 by 2 into x to the power n. So we'll multiply x square. So we can write n minus 1, we'll divide by 2 and we'll multiply x square. So there'll be x to the power n. So it'll be this x square upon 1 minus x cube, where n varies from 2 to infinite, which is the series that we need. Now here the value of x is 1 by 7. So it'll be this 1 by 7 square upon 1 minus 1 by 7 cube. So there'll be 1 upon 7 square, and this is 6 cube by 7 cube. So there'll be 7 upon 216. So answer to this question is 7 upon 216. Now there is this one method which is very useful while solving problems which involve difference of terms of a series or a sequence. And the method is, suppose you have a series, say S, and it is given by A1 plus A2 plus A3 plus AN minus 1 plus AN. What we'll do is we'll write this series again and we'll shift every term by 1. So we'll write A1 here, we'll write A2 here, we'll write AN minus 1 here, and we'll write AN here. Now we'll subtract them. On the left hand side, it'll be 0. Then we'll have this A1 plus A2 minus A1 plus A3 minus A2 up to an minus 1 and then minus an, or we can simply write this an as a1 plus a2 minus a1, a3 minus a2 up to an minus 1. Now we'll have this another series which we can solve by again using difference or by using some other method. And the thing to note here is this series has actually n minus 1 terms. So this method where we are subtracting a series by shifting it with one term is going to give us this nth term of a sequence or nth term of a series. And we can use it to find nth term of an AP. Suppose we have an AP whose terms are A1, A2, A3, AN. Common difference is D. We can write this sum as A1 plus A2 plus AN. We can again write this sum as A1 plus A2, and here will be this AN minus 1 plus AN. Now if we subtract them, we can write 0. It will be this A1 plus, now this is A2 minus A1, this is A3 minus A2, and this is AN minus 1, and this is minus AN. Now we can write this as AN equals, now this is A1. Now we know that difference between any two successive terms, it is simply D, and this series has n minus 1 terms. So this nth term will be A1 plus n minus 1 into D. So this is another way of writing the nth term of an AP. And in general, we take first term as A. So we generally write this as AN equals A plus n minus 1D for an AP. Now we have some special sequences where the difference may not be constant, but the difference of difference may be constant, or we can say first difference is an AP. Say for example, we have the sequence which is A1, A2, A3, A4 up to AN. Now if we take the differences, A2 minus A1 is suppose B1, A3 minus A2 is B2, A4 minus A3 is B3, and these difference, they are constant. B2 minus B1 is D, B3 minus B2 is D. So this first difference becomes an AP. So this series B1, B2, B3, it is an AP. Now we know that if the sequence is an AP, then the terms are linear. But if the first difference are an AP or difference of difference is constant, then the terms are quadratic. So we can take nth term of the series as an square plus bn plus c. Now we'll prove this using that series shifting method. Suppose some of the series is S, so we can write A1 plus A2 plus A3 plus AN. We'll write the series again. We'll shift it by one term. So this is A1, A2, and this is AN minus 1 plus AN. Now we'll subtract them. This is 0. Now this is A1 plus, this is A2 minus A1 plus A3 minus A2 up to AN minus 1, and then minus AN. We'll take this AN on the left hand side. We can write AN, and this is A1. Now A2 minus A1 is B1, A3 minus A2 is B2, and this is going to be Bn minus 1. So it will be the series B1 plus B2 up to Bn minus 1, which is nothing but an AP. So this is sum of an AP. Now this is AN, this is A1, and we know that sum of an AP which has n minus 1 terms will be n minus 1 by 2 twice A, and A in this case is B1 plus n minus 1, which is going to be n minus 2 into D. So this AN will be this A1 plus n minus 1 B1 plus n minus 1 n minus 2 by 2 into D. we can rearrange this as n square d by 2. Now it'll be plus b1 minus 3d by 2n plus a1 minus b1 plus d, which is a quadratic equation in n. So basically its nth term will be a quadratic term. And we have already seen how to solve this. So this is why the terms of the sequence where the first difference are in AP is going to be quadratic. Now we can extend this also. So if we have this sequence A1, A2, A3, A4, A5, and we have their differences B1, B2, B3, B4. Now these differences, they are not constant, but they form an AP now. So suppose it is C1, C2, C3, and these difference, they are constant. So when we have second difference as an AP, then the terms are given by a cubic equation. So there'll be AN cube plus BN square plus CN plus D. And here this D is not the common difference. It is some other number, say D dash. Now we have another special sequence where the difference is in GP. So suppose we have this series A1, A2, A3, A4, A5, and AN. Now these differences, they are B1, B2, B3, B4, and their ratios is same. So B2 upon B1 is R, B3 upon B2 is R, B4 upon B3 is R. So basically their first difference, they are in GP. So when we have a series when their first difference are in GP, then its nth term, it is given by A plus B R to the power n minus 1, where this R is common ratio of this GP. Now we can prove this also using that shifted sum method. So this sum is S. So this is A1 plus A2 plus A3 up to AN. Again, this is A1 plus A2 plus AN minus 1 plus AN. If we subtract, we can write 0, and this is A1. Now A2 minus A1 will be this B1, B2 plus Bn minus 1 and minus AN. So we can simply write this AN as A1 plus, now this is sum of a GP, and we know that sum of a GP is A R to the power n minus 1 minus 1 upon R minus 1. Now we can rewrite this as A1 minus B1 upon R minus 1 and plus B1 upon R minus 1 R to the power of n minus 1. Now this is some constant A and this is some constant B. So its nth term will be of the form A plus B R to the power n minus 1. We can also extend it to the second difference. So if we have a sequence which is given by A1, A2, A3, A4, A5, and suppose the differences are B1, B2, B3, B4, and these differences, they are neither in AP and nor in GP. We'll again take a difference. So suppose the differences again are C1, C2, and C3, and suppose this is a GP with common ratio R. So now we have a GP in second difference. So when second difference are in GP, then the nth term, it is given by AN plus B plus C R to the power n minus 1. So rather than this constant, it will be a linear term here. And if it is third difference is in GP, then we'll have a quadratic term along with R to the power n minus 1. So this is why we choose these terms the way we do. So we can solve these questions using either direct quadratic formula, or we can solve these questions by using this method. So suppose we are given the sequence which is 6, 11, 18, 27, 38, 51, and so on. We have to find its nth term and sum of first n terms. Now, if we look at their difference, 11 minus 6 is 5, 18 minus 11 is 7, 27 minus 18 is 9, 38 minus 27 is 11, and 51 minus 38 is 13, which is an AP. That means their first difference is constant and it is equal to 2. So what we can do is, we'll say this sum is S, and it will be this 6 plus 11 plus 18 up to an. Now we'll write the series again. Here will be this an minus 1 and then plus an. Now we'll subtract this second series from first. It will be 0. Now this is 6 plus 11 minus 6 is 5. 18 minus 11 is 7. 5 plus 7 plus 9. And we know that here we'll have n minus 1 terms. And then minus an, or we can simply write an as 6 plus. Now this is sum of n minus 1 terms of an AP. So it will be this n minus 1 by 2 twice a plus n minus 1, which is going to be n minus 2 into d, and d in this case is 2. Now this 2 and 2 will cancel. So this an will be 6 plus n minus 1 into n plus 3, or we can write n square plus 2n plus 3. We can verify also. So if we put n as 1, we'll get a1. So it'll be this 1 plus 2 plus 3, 6. If we put n as 2, it'll be 4 plus 4, 8. 8 plus 3, 11. a3. So it'll be 9 plus 6, 15. 15 plus 3, 18. So this is your nth term. And if we have to find sum of n terms, it'll be given by this summation AR, and there'll be summation R square plus 2R plus 3, which is summation R square plus 2 times summation R plus summation 3, which is going to be n plus 1 2n plus 1 by 6 plus 2 times n plus 1 by 2 and plus 3n. Now, in first differences, you may get questions in recurring relations as well as in functions. Say, for example, you are given this question where it says 1 plus fx, it is equal to fx minus 1 plus fx plus 1 whole divided by 2. Now, we can write this as fx plus 1 minus 2fx plus fx minus 1, and it'll be equal to 2. Now this is fx plus 1 minus fx, and then minus fx minus 1, and it is equal to 2. Now if we take x as natural numbers, then this is an plus 1 minus an minus an minus 1, and this is equal to 2. Now this is difference between two terms, and this is difference between an and an minus 1. Suppose this is b2. So this successive difference, it is constant, and we know that when successive difference is constant, then the term will be a quadratic term. So this function fx, it will be a quadratic polynomial. So value of in this case will be simply 2.
Today we'll discuss two special sequences. Now generally when we study sequences, we study arithmetic progression, geometric progression, and at times harmonic progression. But then there'll be certain cases where the series in itself is not an AP or GP, but their successive differences, they may be in arithmetic progression or they may be in geometric progression. So here, first we're going to talk about series in which successive differences, they are in arithmetic progression. So suppose we have any progression which is A1, A2, A3, A4, A5, A6, A7. Now if we take the differences, suppose differences are B1, B2, B3, B4, B5, B6. Now if all these differences they are constant, then clearly this series it is an AP, and we know that any AP it can be characterized by a linear term. So we can take its nth term as an plus b. Now if difference is not constant, then what we'll do is we'll take difference of difference. So we'll subtract b1 from b2, say it be c1. Now this is c2. Now this difference, let be c3, c4, c5. Now say this difference is constant. So if difference of difference is constant, then our general term will be a quadratic term. So it will be an square plus bn plus c. So if difference is constant, it is linear term, it will be an AP. If difference of difference is constant, then it will be a quadratic term. If difference of difference of difference this series it is constant, then in that case its nth term will be cubic. So it will be an cube plus bn square plus cn plus d. Now we'll be given at least 4 terms. So we'll put n as 1, we'll write first term. We'll put n as 2, we'll get second term. N as 3, we'll get third term. So using these equations, we can find the values of a, b, c and d. Now let us take up an example. Suppose we need to find nth term and sum of first n terms of the sequence 6, 11, 18, 27, 38 and 51. Now what is the difference? 11 minus 6, 5. 18 minus 11, 7. 27 minus 18, 9. 38 minus 27, 11. 51 minus 38, 13. Now this series, it is not constant but an AP. Now if we take difference again, 7 minus 5 is 2. 9 minus 7 is 2. 11 minus 9, 2. 13 minus 11, 2. So here difference of difference is constant. Now when difference of difference is constant, we know that its general term will be an square plus bn plus c. Now we have 3 unknowns a, b and c. We need to find the value of a, b and c. Now if we put n as 1, we'll get t1 will be a plus b plus c and it will be equal to this first term, that is 6. Now if we'll put n as 2, we'll get 4a plus 2b plus c and there'll be second term, and its third term will be when n is 3, so it will be 9a plus 3b plus c and it is 18. Now what we'll do is we'll subtract first term from second, we'll get 3a plus b and it'll be 5, and if we subtract second from third, we'll get 5a plus b and it'll be 7. Now again we'll subtract first from second, we'll get 2a equals 2, so value of a is 1. So here the value of a is 1. Now if we'll put a as 1, we'll get b as 2. So here value of a is 1 and b is 2. Now if a is 1 and b is 2, then the value of c is 3. So now we have a, b and c. So we can write its general term. So its general term tn will be an square. So it will be n square plus bn, b is 2. So plus 2n and plus 3. So this sequence is generated by this general term, which is n square plus 2n plus 3. Now we'll put n as 1, we'll get 6. We'll put n as 2, so 4 plus 4, 8, 8 plus 3, 11, 9 plus 6, 15, 15 plus 3, 18. So for this sequence, nth term is n square plus 2n plus 3. Now, if we have to find sum of n terms, we know that sum of n terms is nothing but summation tr. So, it will be summation n square, summation 2n, and summation 3. Now, summation n square is n plus 1, 2n plus 1 divided by 6, then 2, and here summation n is n plus 1 by 2, and then plus summation 3 is 3n. So that is the sum of first n terms of this sequence. So if difference of difference is constant, then we take these terms as a quadratic term. Now let us take another example. Say for example, the sequence is given by 1, 4, 10, 20, 35, 56 and so on. Now we'll find its difference. So it'll be 3, 6, 10, 15, 21. Now difference is not constant. We'll again take the difference. 6 minus 3 is 3. 10 minus 6 is 4. This is 5. This is 6. Now again we'll take difference. So it'll be 1, 1 and 1. Now here difference of difference of difference is constant. So if difference of difference of difference is constant, then we know that our nth term will be a cubic term. So it will be an cube plus bn square plus cn plus d. Now if we put n as 1, we'll get a plus b plus c plus d. It will be its first term 1, and then if we'll put n as 2, so it will be 8a plus 4b plus 2c plus d. It will be 4. If we'll put n as 3, so it will be 27a plus 9b plus 3c plus d. It will be 10. And then if we'll put n as 4, so it will be 64a plus 16b plus 4c plus d equals. Now if we'll solve these 4 equations, we'll get the value of a as 1 by 6, value of b as 1 by 2, value of c as 1 by 3, and value of d as 0. So its general term will be given by 1 by 6 n cube plus 1 by 2 n square plus 1 by 3n. And that is the answer to this question. Now, what if the difference is not an AP? Difference is in GP. Now, if we have any sequence, say A1, A2, A3, A4, A5, A6 and A7, and suppose this sequence, it is in GP with common ratio R, we know that its general term is given by A into R to the power n minus 1. Now, suppose the sequence is not in GP, we'll find their differences, say B1, B2, B3, B4, B5, B6. Now, suppose for this series, difference is in GP. If difference is in GP, then its rth term is given by A plus B into R to the power n minus 1. Now, suppose difference is not in GP, then we'll again take the difference. Say this is C1, C2, C3, C4, C5. Now, suppose difference of difference is in GP. So, if difference of difference is in GP, we can take this rth term as an plus b and c into r to the power of n minus 1, where r in each case is common ratio of GP. Now, let us take up an example. Say, for example, suppose we are given a sequence 4, 5, 7, 11, 19 and 35. Now, this is neither an AP nor a GP. We'll find its difference. So its difference will be 1, 2, 4, 8, 16. Now this difference is in GP with common ratio 2. Now if difference is in GP, we know that its general term is given by Tn will be a plus b r to the power of n minus 1. So its general term Tn will be a plus b, and what is the value of r? R here is 2, so it will be 2 to the power of n minus 1. Now we'll put n as 1, we'll get a plus b, and it'll be its first term. So it'll be 4. Now we'll put n as 2, we'll get a. Now if we'll put n as 2, it'll be 2b, and then it'll be t2 second term, which is 5. Now we'll subtract. We'll get value of b as 1, and if the value of b is 1, value of a is 3. So for this series, its general term Tn, it is given by 3 plus 2 to the power of n minus 1. Now we'll put n as 1, we'll get 4. If we'll put n as 2, 3 plus 2, 5. 3 plus 4, 7. 3 plus 8, 11. This is how we generate nth term for the sequence if successive differences they are in GP. Let us take another example. Now suppose the question is, we need to find sum of first 8 terms of the sequence 2, 5, 12, 31, 86. Now first we'll find its difference. Difference is 3, 7, 31 minus 12, 19, 55. Now this difference, it is neither an AP nor a GP. Now we'll find successive difference. Now 7 minus 3 is 4. 19 minus 7 is 12. 55 minus 19 is 36. Now this sequence, it is GP. So this successive difference, it is in GP and its common ratio is 3. So if successive difference is in GP, we know that its general term Tn will be given by An plus B plus C into R. R here is 3, so it will be 3 to the power of n minus 1. So this is how we can define its general term. Now we need to find the value of A, B, C. Now if we'll put n as 1, we'll get first term, so it will be A plus B plus C, and it will be equal to 2. For n equals 2, it will be 2A plus B plus 3C, and that is second term 5. And if we'll put n as 3, we'll get 3A plus B plus 9C, and it will be 12. Now we'll subtract first from second, we'll get A plus 2C equals 3, and we'll subtract second from third, we'll get A plus 6C equals 7. Now we'll subtract again first from second, we'll get 4C equals 4, value of C is 1. Now we'll put C as 1, we'll get A as 1. Now C is 1, A is 1, then the value of B is 0. So for this sequence, its general term will be given by n plus 3 to the power n minus 1. Now we need to find sum of first 8 terms. So sum of first 8 terms, it will be summation TR. R varies from 1 to 8. So it will be this summation R and then summation 3 to the power of R minus 1. Now summation R will be n plus 1 by 2, and then this is nothing but a GPs. It will be 1, 3, 3 square up to 3 to the power 7. So it will be A R to the power n minus 1 by 2. This sum, it will be 3316. So sum of first 8 terms of the sequence will be 3316.
Today we'll discuss a shortcut which is used in the problems where difference of difference is constant. So you'll find many problems in which you'll be given a series such as A1, A2, A3, A4, A5. Now in this series, if we find the difference, so A2 minus A1 is D1, A3 minus A2 is D2, A4 minus A3 is D3, A5 minus A4 is D4. So this is your difference series. And if we take difference of difference, that is D2 minus D1 as D, D3 minus D2 as D, and D4 minus D3 is D. So in this case, difference of difference is constant. So we'll get many cases in which difference of difference will be constant. Now,
In this case, we know that its nth term will be given by a quadratic term. So it will be an square plus bn plus c. Now first we'll look at its standard way of solving the question, and then we look at the shortcut. Now in order to find ABC, we'll need to find three equations. So what we'll do is we'll put n as 1, and if we put n as 1, we'll get a plus b plus c, and it will be equal to t1, and t1 is nothing but its first term. So it will be this a1. Now if we put n as 2, we'll get this as 4a plus 2b plus c, and it is t2, and t2 is your second term, which is a2. And if we put n as 3, so we'll get this as 9a plus 3b plus c, and that will be equal to a3. So now we have three equations and three unknowns. We need to find the value of a, b and c. Now what we'll do is we'll subtract first from second. We'll get 3a plus b equals a2 minus a1, and a2 minus a1 is nothing but d1. In the same way, we can subtract second from third. We get 5a plus b, and that will be equal to a3 minus a2, and that will be equal to d2. Now we have equations in a and b. In order to find this a, we'll subtract this first equation from second. So from here we can write 2a equals d2 minus d1, and d2 minus d1 is nothing but d. Now what is the shortcut here? Shortcut here is once we have this series, we can find their difference and we can find their successive differences. Now this constant difference d, it is nothing but 2a. So we'll simply write this as 2a. Now d1 is nothing but 3a plus b. So we'll write this as 3a plus b. And here this a1 is a plus b plus c. So here this is a plus b plus c. So from here we'll get the value of a, and if we put the value of a here, we'll get the value of b, and from a and b we can get the value of c. Now let us take one example. Say for example we are given this sequence, which is 6, 11, 18, 27, 38, 51. We need to find its nth term. Now if we take the difference, 11 minus 6 is 5, 18 minus 11 is 7, 27 minus 18 is 9, 38 minus 27 is 11, and 51 minus 38 is 13. Now if we take the difference, this is 2, this is 2, this is 2, and this is 2, which means difference of difference is constant. Now we'll use the shortcut directly. Now this is 2a, this is 3a plus b, and this is a plus b plus c. Now clearly a is 1, and if we put a as 1 here, we'll get b as 2, and if we put a and b as 1 and 2, then value of c is 3. So nth term of the sequence, it will be simply n square plus 2n plus 3. Let us take another example. We are given the series 6, 13, 22, 33. Now 13 minus 6 is 7, 22 minus 13 is 9, 33 minus 22 is 11. Now again 9 minus 7, 2, 11 minus 9, 2. So we can write 2a as 2. Now this is 3a plus b, it is equal to 7, and a plus b plus c, it is equal to 6. Now clearly a is 1, and if we put a as 1, we'll get b as 4, and if a and b are 1 and 4, value of c is 1. So value of c, it will be 1. So nth term for this series, it will be n square plus 4n plus 1. And that is the answer to this question. Now let us take another question. And here we need to find the sum of the series up to infinite terms. Now what we'll do is we'll find sum up to n terms. Now in the numerator, we have this series 2, 6, 12, and 20, and so on. We'll write the differences. 6 minus 2, 4. 12 minus 6, 6. 20 minus 12, 8. Now this is 2 and this is 2. Now we can use the shortcut. This is 2a. This is 3a plus b. And this is a plus b plus c. Now clearly a is 1. And if we put a as 1, we get b as 1. And if we put a and b as 1, we get c as 0. So its nth term will be n square plus n. Now in order to solve this question, we have to write general term of the series. It is TR, and it will be in the numerator we'll have r square plus r. In the first term it is 1 cube, second term it is 1 cube plus 2 cube. So it will be 1 cube plus 2 cube up to r cube.
Now we can write this as TR equals R into R plus 1, and this is R plus 1 by 2 whole square. As R plus 1 will cancel, so it will be 4 upon R plus 1, which we can also write as TR equals 4, and this is 1 upon R minus 1 upon R plus 1. Now we need to find sum of n terms. So Sn, it will be 4. Now we put T as 1, it will be 1 upon 1 minus 1 upon 2. If we put T as 2, it will be 1 upon 2 minus 1 upon 3. 1 upon 3 minus 1 upon 4. I will continue up to 1 upon n minus 1 upon n plus 1. Now here 1 by 2, 1 by 3 will cancel. So what we'll get is Sn equals 4 into 1 minus 1 upon n plus 1, which is 4n upon n plus 1. Now we need to find sum up to infinite. Now S infinity is limit n tends to infinite, Sn. Now here highest power of n is 1. So its answer is 4 upon 1, which is simply 4. And that is the answer to this question.
Now you'll find certain problems where recurrence is going to lead to AGP. So we are dealing with recurrence sequence leading to AGP. So if we consider recurrence of the form AN, and this is equal to sum R AN minus 1 plus alpha n plus beta. Now this R, it relates with common ratio of a GP, and this alpha n plus b linear term, it relates with an AP, and two successive terms, they are related like this. So we'll get GP behavior from R and AP behavior from alpha n plus beta. So what we'll do is we'll write this alpha n plus beta as sum Fn. So we can write An as R An minus 1 plus Fn. Now we can write An minus 1 as R A n minus 2 plus Fn minus 1, and we can substitute this An minus 1 here. So it will be this An equals R into R An minus 2 plus F n minus 1 plus Fn. So this An will be R square An minus 2 plus Rf n minus 1 plus Fn. Now we can expand An minus 2. It will be Ra n minus 3 plus F n minus 2. And if we put it here, we'll get this as An equals R cube An minus 3 plus R square Fn minus 2 plus Rfn minus 1 plus Fn. And if we continue like this till A1, we can write this as An equals R to the power n minus 1 A1 plus R to the power n minus 2 F2 R to the power n minus 3 F3 up to Fn, or simply An is R to the power n minus 1 A1 plus this summation where k varies from 2 to n R to the power n minus k Fk. Now this Fk, it is a linear part, so it's an AP, and R to the power n minus k, it is a GP. So in this recurrence relation, finding this n terms, it led to this AGP. So if we take a simple example, we are given this recurring relation an is 2an minus 1 plus n, and it says value of a1 is 1. Now we can write this an as 2 times, and an minus 1 is 2a n minus 2 plus n minus 1 plus n. So this an, it will be 2 square an minus 2 and plus 2n minus 1 plus n. If we write it for an minus 3, we can write this as an will be equal to 2 cube an minus 3 plus 2 square n minus 2 2n minus 1 plus n. And if we keep doing it for n times, we can simply write this as an equals 2 to the power n minus 1 a1 plus 2 to the power of n minus 2 into 2 to the power of n minus 3 into 3 up to 2n minus 1 and plus n. Now this part, it is an AGP. Now to solve this question, we have to solve this AGP, and here the value of a1 is 1. So we can write this as an equals 2 to the power of n minus 1 plus 2 to the power of n minus 2 into 2 to the power of n minus 3 into 3 up to 2n minus 1 plus n. Now we'll write the series again, but by shifting one term, so it will be 2 to the power n minus 1. This is 2 to the power of n minus 2 into 2. And here will be this 2n minus 1 and plus n. Now here the common ratio of GP is 1 by 2. So we'll multiply it with 1 by 2. So here will be this 2 to the power of n minus 2. Here will be 2 to the power of n minus 3. And this one, it will be simply n minus 1. Now if we subtract second from first, we can write 1 by 2 an will be 2 to the power of n minus 1. Now this is 2 to the power of n minus 2. This is 2 to the power of n minus 3. And in the end, we'll have this as 1. And then minus, we'll have 1 by 2 here. 1 by 2n. Now this is nothing but a GP. So this is 1 by 2 an will be 2 to the power of n minus 1 minus 1 by 2n. Now 2 will cancel. So we'll get this an as 2 to the power of n plus 1 minus 2 minus n. So this is the nth term of the sequence given by this recurring relation. So this is how we connect AGP to the recurring relation of the types an equals r an minus 1 plus alpha n plus beta, where this r will correspond to the GP and this linear part will correspond to the AP. And the first formula is this summation r varies from 1 to n, summation 1. Now this is simply summation of a constant, and we know that this is 1 into n, so it'll be simply n. Second formula is this summation r varies from 1 to n, summation r, and the formula here is n plus 1 by 2. We'll prove all these formulas later, but as of now, you must remember these results. Third is this summation r varies from 1 to n, summation r square, and this is n plus 1, 2n plus 1 divided by 6. And fourth is this summation r cube, and this is n plus 1 by 2 whole square, and this also can be expressed as this summation r varies from 1 to n summation r whole square. Now this first formula is very simple, and it is simply summation of a constant. We'll prove the second result here, and third and fourth we'll prove them later. Now we know that we have this sum, and it is this summation r varies from 1 to n r, and this is nothing but this is sum of first n natural numbers. So this summation r is sum of first n natural numbers. Now we can write this sum in reverse also. So it will be when r varies from 1 to n, and we'll replace r with n minus r plus 1. So when r is 1, it will be this n and then n minus 1. We'll continue up to 2 plus 1. Now if we add these two, we'll get 2s, and if we can split summation, we can add them also if they're same starting and end points. So then it'll be this r plus n minus r plus 1. Now this r and r, it'll cancel. So you'll get 2s, and it'll be this summation r varies from 1 to n plus 1. Now there is no r here. So this n plus 1, it is constant. So this is summation of constant. So we can write 2s. It'll be n plus 1 into n, or this sum will be simply n into n plus 1 by 2. So sum of first n natural numbers, that is 1 plus 2 plus 3 up to n, it is given by n into n plus 1 by 2, and which also gives us this result, that is summation r, where r varies from 1 to n, it is n into n plus 1 by 2. Now we'll look into how do we use these standard summation formulas. Suppose we want to find sum of first n even numbers. So second result that you want is sum of first n even numbers. Now we want this 2 plus 4 plus 6 up to 2n. Now we can write this as this summation, and any even number, it can be expressed as 2r. Now this index, it starts from 1 and it goes up to n. Now we can take this constant out, so it will be this 2 into summation r varies from 1 to n summation r, and we know the formula for summation r, it is n plus 1 by 2. So this sum of first n even numbers will be simply n square plus n, or n into n plus 1. In the same way, we can write sum of first n odd numbers. Now this is 1, 3, 5 up to 2n minus 1, and that's your general term. We have seen it in odd sequences. So this is this summation r varies from 1 to n, and this is general term, which is 2r minus 1. Now we can split it as 2 times summation r minus summation 1. Now summation r is n plus 1 by 2. We know this formula, and minus summation of constant is simply n. So it will be this n square plus n minus n. So this is n square. So we have this important result, sum of first n odd numbers is simply equal to n square. And very rarely we use this formula for summation r to the power 4, where r varies from 1 to n. So this is sum of fourth power of natural numbers. So this is 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4 up to n to the power 4. and this is n plus 1, 2n plus 1, 3n square plus 3n minus 1 whole divided by 30. Now we are not going to prove this result, but if you want, you can prove this result using principle of mathematical induction. The proof is simple, but it'll involve a lot of calculation. So now we'll take some examples on how to use these formulas. Say for example, you have to find this summation. R varies from 1 to n 2r square plus 3r plus 1. Now we can use properties of summation. So there'll be 2 into summation r square plus 3 into summation r plus summation 1. Now formula for summation r square is n plus 1 2n plus 1 by 6. Formula for summation r is n plus 1 by 2, and then summation 1 will be simply n. We can find some with shifted powers also. Say for example, we need to find this summation. R varies from 1 to n r plus 1 square. So there are two ways of solving it. One of the method is by expansion, so we can expand it. So we can write r varies from 1 to n, and this is r square plus 2r plus 1. So it will be this summation r square plus 2 times summation r plus summation 1. Now this is n plus 1 2n plus 1 whole divided by 6 plus 2 times n plus 1 by 2 and plus n. So this is one method of doing it. Or we can solve this question by changing the index. So let k equals r plus 1. So it will be this summation k square. Now when r is 1, this is 2. And when r is n, so it will be this n plus 1. So k starts from 2 to n plus 1. But in the formula, our formula starts from 1. So what we'll do is we'll add 1 square and we'll subtract 1 square. So if we add 1 square, we can change this as k varies from 1 to n plus 1, k square. And then since we have added 1 square, we have to subtract 1 square also. So we have this summation and this minus 1 square. Now this is the formula for summation r square. But here the ending value is not n, it is n plus 1. We'll use the formula for summation r square, which is n plus 1 to n plus 1 by 6. But we have to replace n with n plus 1. So it will be n plus 1 into n plus 2 and then 2n plus 1 plus 1. So there will be 2n plus 3 whole divided by 6 minus 1. Now, initially, many of the students, they falter when the summation actually starts from 0. So you may get this summation r varies from 0 to n ar. Now, in this case, we don't have n terms because it's not starting from 1, it's starting from 0. So number of terms in this, it is n plus 1 and not n. So in this case where this is r varies from 0 to n, summation r. Now when you put r as 0, it will be 0 plus 1 plus 2 up to n. It won't make a difference. It will be same n plus 1 by 2. But if we have this summation r varies from 0 to n and say 1. Now this is not n. This is 1 plus 1 plus 1 n plus 1 times. So here it will be this n plus 1. Then we may have some questions where you'll be given this summation where value of r, it starts from some random value, say from m to n, and this is ar. Now what we can do is we can write this as this summation r varies from 1 to n AR. That is, from 1 to n we have all the terms, and from this we'll subtract all the terms from 1 to m minus 1. So say for example, if we are asked this summation r varies from 5 to n r square, we can simply write this as this summation r varies from 1 to n r square minus this summation r varies from 1 to 4 r square. Now we already have this formula, so it will be this n plus 1 to n plus 1 by 6, and then this is simply 1 square plus 2 square plus 3 square plus 4 square, which is 30. So we can simply replace this with 30.
Now here the question is, let TR be the rth term of an AP whose first term is minus 1 by 2. So first term is minus 1 by 2 and common difference is 1. Now its rth term will be A plus r minus 1 into D, which is r minus 3 by 2, or we can write simply 2r minus 3 by 2. Now TR plus 1th term will be 2r minus 1 by 2. TR plus 2th term will be 2r plus 1 by 2, and TR plus 3rd term will be 2r plus 3 by 2. Now it says we need to find this series, which is summation r varies from 1 to n under root of 1 plus TR plus 1, TR plus 2, and TR plus 3. That will be this summation r varies from 1 to n, and this is under root of 1 plus, and this is 2r minus 3 into 2r minus 1, 2r plus 1, 2r plus 3 upon 16. Now this is a plus b into a minus b. So we can write this sum as this summation r varies from 1 to n, and it will be this under root of 1 plus, and this is 4r square minus 1 into 4r square minus 9 whole divided by 16. Now we take 1 by 4 common, and it will be this summation r varies from 1 to n, and here it will be this 16 plus 16 r to the power 4 minus 10 into 4r square plus 9. Now this is 1 by 4 summation r varies from 1 to n, and it will be this 4r square whole square minus 10 into 4r square plus 25. So this is a square plus b square minus 2ab, and which is a minus b whole square. So it will be this 1 by 4, and then summation r varies from 1 to n 4r square minus 5. Now this sum will be 1 by 4, and 4r square is n plus 1, 2n plus 1 whole divided by 6, and minus 5n. So this sum, it will be n plus 1, 2n plus 1 by 6, and minus 5n by 4. And that's your option A.
Now here the question, we are given a function fx, which is this quadratic polynomial, which is ax square plus bx plus c, and it says a plus b plus c, it is equal to 3, and fx plus y, it is equal to fx plus fy plus xy for all xy belongs to R. We need to find this summation. N varies from 1 to 10 Fn. Now we'll use this result fx plus y equals fx plus fy plus xy. So now fx plus y will be a x plus y whole square plus b x plus y plus c, and will be equal to fx. So it will be this ax square plus bx plus c, and plus fy will be ay square plus by plus c plus xy. Now we can write this as a x square plus y square plus 2axy plus b x plus y plus c, and it will be equal to a x square plus y square plus xy plus b x plus y plus 2c. Now we compare 2axy with xy. Value of a will be 1 by 2 and c equals 2c. That means value of c is 0. Now we'll put the value of a and c here. So if a is 1 by 2 and c is 0, we'll get b as 3 minus 1 by 2, and that will be 5 by 2. So that means this function fn, it will be 1 by 2 n square plus 5 by 2n. Now we need to find this summation fn, where n varies from 1 to 10. So it will be this 1 by 2 summation n square plus 5 by 2 summation n. Now this is 1 by 2, value of n is 10. So it will be n plus 1, 2n plus 1 whole divided by 6 plus 5 by 2 n plus 1 by 2. Now this is 7 and this is 4, 770, and this is 550. So we have 770 and 550. So this is 1320 by 4, and will be 330, and that's your option 2. Now the question is, we are given this series which is under root of a1 plus under root of a2 minus 1 plus under root of a3 minus 2 up to under root of an minus n minus 1, and this is 1 by 2 a1 plus a2 up to an minus n minus 3 by 4. Now what we'll do is, on this right hand side we'll write this as 1 by 2 a1, we'll write a2 minus 1, a3 minus 2, and an minus n minus 1. And since we are subtracting them, we'll also need to add 1 plus 2 plus 3 up to n minus 1, and this is minus n minus 3 by 4. So this is under root a1 plus under root of a2 minus 1 under root of a3 minus 2 up to under root of an minus n minus 1, and here will be this 1 by 2. We'll take 1 by 2 common from everything, and we'll have this under root a1 square plus under root a2 minus 1 square up to under root an minus n minus 1 square, and here will be n plus 1 by 2. So it will be n minus 1 n by 2 minus n minus 3 by 4. Now we'll multiply this 2 on the left hand side and we'll simplify this. So it will be this 2 times under root a1 plus 2 times under root a2 minus 1 plus 2 times under root an minus n minus 1, and here we'll have under root a1 square under root a2 square under root an minus n minus 1 square, and here it will be n by 2 and then n minus 1 minus n plus 3. So it will be this 2. So this is simply n. And what we'll do is we'll write this n as plus 1 plus 1 plus 1 with each of these n terms, and we'll take these on the right hand side. So we can write under root a1 square minus twice under root a1 plus 1, which becomes a perfect square. In the same way, under root of a2 minus 1 whole square minus 2 under root of a2 minus 1 plus 1, which again is a whole square, and in the end will be under root of an minus n minus 1 whole square minus twice under root an minus n minus 1 plus 1, and this should be equal to 0. So this is root a1 minus 1 square. This is root a2 minus 1 minus 1 square, and will be root an minus n minus 1 minus 1 whole square, and it is 0. Now sum of perfect squares is 0 when each of this term is 0. So a1 is 1, a2 is 2, and an is n. So basically AR is R. Now we need to find this summation. Summation I varies from 1 to 100 AI, and it will be simply this summation I. So it will be 100, 101 divided by 2. So this is 50. So it will be this 5050. So value of this summation is 5050, and that is the answer to this question. Now the question is, we need to simplify this summation, which is R varies from 1 to n summation R square minus summation m varies from 1 to n summation R varies from 1 to m summation R. Now first we simplify the summation R. We can write summation R varies from 1 to n R square minus, and this is summation m varies from 1 to n, and this is m plus 1 by 2. So basically this is summation R varies from 1 to n R square minus, and it is 1 by 2 summation m varies from 1 to n m square minus 1 by 2 summation m varies from 1 to n summation m. Now limit of summation goes to 1 to n, then this variable, it doesn't matter. So what we'll do is, rather than taking it as m, we'll write it as r. So we can write simply summation r varies from 1 to n r square minus 1 by 2 summation r square r varies from 1 to n minus 1 by 2 summation r varies from 1 to n. Now this is 1 by 2 r square. So we can write this as 1 by 2, and then it will be simply summation r square r varies from 1 to n minus summation r varies from 1 to n, and that's your option C. Now it should be r here. R varies from 1 to n r to the power 4. It is equal to fn. That means 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4 up to n to the power 4 is fn. We need to find this sum. Summation r varies from 1 to n 2r minus 1 to the power 4. So we need to find 1 to the power 4 plus 3 to the power 4 plus 5 to the power 4 up to 2n minus 1 to the power 4. So what we'll do is, we'll start with f to n, and f to n will be 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4 up to 2n to the power 4. Now here again we separate even and odd terms. So we write odd terms together, 1 to the power 4 plus 3 to the power 4 and plus we'll have 2 to the power 4 plus 4 to the power 4 up to 2n to the power 4. Now this is the required summation that we need. So we can write f2n and ab equal to this summation. R varies from 1 to n 2r minus 1 to the power 4, and here we'll take 2 to the power 4 common, so it will be the 16, and then 1 to the power 4 plus 2 to the power 4 up to n to the power 4, which is nothing but fn. So this is fn. So from here we can say this summation r varies from 1 to n 2r minus 1 to the power 4 will be equal to f2n minus 16 fn for all n. So the correct option is this option A. Now here the question is, we need to find value of secant inverse of 1 by 4 summation k varies from 0 to 10 secant 7 pi by 12 plus k pi by 2 into secant 7 pi by 12 plus k plus 1 pi by 2, which we will write as 7 pi by 12 k pi by 2 plus pi by 2. Now we'll change them in cos, so we can write secant inverse 1 by 4, and then this summation k varies from 0 to 10, and this is 1 upon cos 7 pi by 12 plus k pi by 12, and this is cos 7 pi by 12 plus k pi by 12 and plus pi by 2. Now cos 90 plus theta is minus sine theta. So we'll take minus sign, so it will be this secant inverse. We'll take minus sign out, and then we have this summation k varies from 0 to 10, and it will be 1 upon cos 7 pi by 12 plus k pi by 2 into sine 7 pi by 12 plus k pi by 2. I will multiply and divide it with 2. Now this is 2 sine A cos B. So it will be sine 2A, and this 2 and 1 by 4 will cancel. So we'll get this as secant inverse minus 1 by 2, and then this summation k varies from 0 to 10. This is 1, and it will be sine 2 theta. So there will be sine 14 pi by 12 plus k pi. Now we can write this as secant inverse minus 1 by 2, and then summation k varies from 0 to 10, and this is 1 upon. Now this is 7 pi by 6 plus k pi. So we can write this as 7 pi by 6 equals pi plus pi by 6. So it will be this sine k plus 1 pi plus pi by 6. Now we know that sine n pi plus theta, it is minus 1 to the power n sine theta. If n is odd, we'll have minus sign, and if n is even, we'll have this plus sign. So we can write this as secant inverse minus 1 by 2, and then summation k varies from 0 to 10, 1 upon minus 1 to the power k plus 1 into sine pi by 6. Now sine 30 is 1 by 2, so this 1 by 2 and 1 by 2 will also cancel. So this expression will be secant inverse minus, and then this summation k varies from 0 to 10 minus 1 to the power k plus 1. Now this is secant inverse minus
and we'll have alternate plus minus signs. And there are 11 terms, so 10 of these terms they'll cancel, and then we're left with this first term. When k is 0, if we put k as 0, we'll get this as minus 1. So it is nothing but it is secant inverse 1, and we know that secant inverse 1 is 0. So answer to this question is simply 0. Now here we are given two questions, and for these two questions we have to find their nth term and sum of n terms. Now this first question is, we have the series 1 plus 5 plus 13 plus 29 plus 61 up to n terms. Now here difference is 4, 8, 16, 32, which is a GP. So this difference, it is in GP with common ratio 2. So we have this common ratio of 2, and we know that if difference is in GP, then its general term, it is written as a plus b into r to the power n minus 1, and r in this case is 2. So it will be this a plus b into 2 to the power of n minus 1. Now here we have two unknowns a and b. We put n as 1, it will be this a plus b, and it will be 1. And if we put n as 2, it will be a plus 2b, and it is 5. Now we subtract, we'll get b as 4, and if b is 4, value of a is minus 3. So its general term will be minus 3 plus 4 into 2 to the power of n minus 1, or it is minus 3 plus 2 to the power of n plus 1. Now we need to find sum of n terms. Now this Sn will be simply this summation r varies from 1 to n tr, which is this summation r varies from 1 to n minus 3 plus 2 to the power of r plus 1. Now summation of minus 3 simply minus 3n, and then we'll have this summation r varies from 1 to n 2 to the power of r plus 1, which is nothing but a GP. Now for this GP, this first term is, when you put r as 1, which is 4, common ratio is 2, and number of terms is n. So we can write this as minus 3n, and this is 4 into 2 to the power n minus 1 upon 2 minus 1. So it will be this minus 3n plus 2 to the power of n plus 2 minus 4. And that's the answer to this first question. Now this second question is, we need to find sum of this series and its nth term, 6, 13, 22, 33. Now here difference is 7, 9, 11. Now difference of difference is constant. We know that its nth term, it will be an square plus bn plus c. Now we'll use the shortcut. This is 2a, this is 3a plus b, and this is a plus b plus c. Now clearly a is 1, and if we put a as 1, we'll get b as 4, and if we put a as 1 and b as 4, we'll get c as 1. So its general term or its nth term will be n square plus 4n plus 1. Now we need to find sum of n terms, and there will be this summation r varies from 1 to n tr. So it will be this summation r varies from 1 to n, and there will be r square plus 4r plus 1. Now summation r square is n plus 1, 2n plus 1 by 6 plus, and this is 4 n plus 1 by 2, and then plus n. Now we'll simplify these two. What we'll do is, we'll take n plus 1 by 6 common. So we'll have 2n plus 1 plus 12 plus n. So it will be this n plus 1, 2n plus 13 upon 6 plus n, and that is the answer to this question.
Now here the question is, we are given a number which is of the form 7, 5, 5, 5, 7, and here we have total R5s, and then we have these two numbers 7, so basically it is R plus 2 digit number. So first and last digit are 7 and remaining digits are 5. So consider the sum as, which is 77 plus 757 plus 7557, and goes all the way up to 75557, and here we are taking them 98 times. So basically it's a 100 digit number. Now it says we have to express this sum as 7 and then 99 times 5, 7 plus m by n, where m and n are natural numbers less than 3000. Find the value of m plus n. So somehow we have to solve this series. Now generally when I see this pattern, I know we have to use difference somewhere. So what we'll do is we'll write 10s. So we'll multiply this series with 10 and we'll shift the series by 1 unit. So here it will be 770. Here it will be 7570. And this term here will be 755570. So here we have 98 5s and then we have 70. Now what we'll do is we'll subtract first from second. So if we subtract first from second, now 10s minus s is basically 9s. Now this is minus 77. Now 770 minus 757. Essentially this is 70 minus 57. So it will be this 13. Now here also 75. It's of no use. 70 minus 57 is again 13. I'll continue up to this term, which is 13 plus this 7, 555, 98 times, and then this is 70. Now first thing is, how many 13s do we have? So we have started with 1 and we have gone up to 98 5s. So this 13, it appeared 98 times. So we can write this 9s will be minus 77 plus 13 into 98 plus, now here we need 7, 5, 5, 5, 5, 5, 7, 99 times. So what we'll do is, we will subtract 13 and we'll add 13. So here we'll add 13, and if we subtract 13, it'll become 7, 5, 5, 5, 5, 7, and now this is 99 times 5. So basically this is 9s and this is 13 into 99 minus 77 plus 7, 5, 5, 5, 7, 99 times, which we need in the question. So it will be 1210 plus 7, 5, 5, 5, 5, 99 times 7, or we can write this as 1210 plus 7, 5, 5, 5, 5, 99 times 7 whole divided by 9. Now we have put it in this form. Now this is your m and that's your n. We
we need to find the value of m plus n. So value of m plus n is 1210 plus 9. So there will be 1219, and that is the answer to this question.